obtaining best solution or best result under given restriction. So in several decision making problem or engineering design problems, so we have to take many technological and managerial decision at several stages. So this objective of such decision, as you know, either to maximize the effort required or to maximize the desired, minimize the effort required or to maximize the benefit. Either you minimize or maximize. The optimum seeking methods are known as optimization technique. This is also a part of the operation research. As I have told, operation research, this is the art of finding the best solution for the business operation is known as operation research. So UR is also a branch of mathematics concerned with some technique for finding best solution. Mainly we will discuss in this operation research what are the techniques, what are the algorithms we used to find the solution. Okay, what are the techniques as well as what are the algorithms. So just I like to mention few applications in the real life problem, in some engineering design problem. For example, optimal design of solar system, electrical network design, energy model and planning, optimal design of component of the system, planning and analysis of existing operation, optimal design of motors, generator, transformer, etc. Design of aircraft for minimum weight, optimal design of bridge building. These are the engineering application, and it has application in management science, in the social science, in mathematics. In every area, it has some applications. Depends on the use, depends on the requirement. We use the model and you find the solution. Okay. See, as I already mentioned, in this operation research, so we will discuss about mainly about the linear models. Linear model in the sense, so in a mathematical model, we have some objective function, we have some constraints, we have some decision variables. So using the objective function, constraints and the decision variables, we formulate the models. So mainly we'll discuss about the linear models, and sometimes if the model is not linear, other than linear, we name it non-linear models. Okay, so this will be discussed in different courses. Okay, so first let us consider a linear models. The linear model, the statement is like this. See, I have already mentioned, so either you maximize or we minimize. Okay, so I'm considering a model, a mathematical model, where we want to maximize what? Maximize maybe the profit, maybe the production, maybe the benefit, etc. So here the model, as you know, I'm saying Z, a linear function of X. There are n number of decision variables, and what we are going to find? We are going to find the unknowns x1, x2, x3 up to xn. These are the unknown variables, unknown decision variables, or known as unknown control variables. We like to find out which will maximize the objective function Z equal to summation over j varies from 1 to n Cj xj. This is our objective function. subject to some constraints. Say what the constraints say about the problem. We have limited resources, limited time, limited space. See, some restriction is imposed on the problem. With respect to the restriction, we are interested to find the maximum value of the objective function. Subject to here, summation over j varies from 1 to n aij xj less than or equal to bi, I varies from 1 to up to m. And what about the decision variables? These variables x1, x2, xn, generally in a linear programming problem, they are non-negative in nature. Non-negative in nature. In some problem, if you find the decision variables x1, x2 up to xn are either binary or integer, they are different type of problem. So that also will be discussed. So here, these decision variables x1, x2, xn, they are non-negative in nature. Non-negative. They can take integral value, they can take decimal value or fractional value. So, but they cannot take negative value. They are non-negative in nature. Generally, this is a model we like to discuss, and we like to solve such models in the linear programming. Okay. See, these models. So, as I already mentioned, either it is a maximization type model or maybe it is a minimization type model. So I am just naming two different models. One is maximization type, let us say model 1. We want to maximize z. Okay, summation over j varies from 1 to n cj xj. Subject to restriction is like this. Summation over j varies from 1 to n aij xj less than or equal to bi. I varies from 1 to up to m, and all the x are non-negative. This is a typical case of a maximization type model. We can name as this model as LPP model 1. Okay. So similarly, we have also minimization type model. If maximization type models are there, then we can have also minimization type model. How the model looks like? The minimization type model. The model is like this. Minimize instead of maximizing, we are minimizing a objective function z. Summation over j varies from 1 to n cj xj. Subject to, for the, as you know, for the maximization type model, generally the constants are less than equal type. For the maximization type model, these constants are less than equal type. This also can be greater than equal type or equal type or can be any type. But generally, for maximization type linear programming problem, the constants are less than equal type. Similarly, for the minimization type objective function, if you are taking LPP model 2, then we have these constants are generally greater than equal type. So the right hand side, whatever the BI is given, generally this BI are non-negative in nature, this BI. Similarly, earlier calls also this BI. So this is the resources level. So it is also, this BI is also non-negative. Okay, this, the model 1 and model 2 we have discussed. So now, generally, this linear programming problem we solve using linear system. So the linear, system of linear equation we are solving. So whenever you are solving a system of linear equation, let us say the system is non-homogeneous. Non-homogeneous means the right hand side is non-zero. If the right hand side is 0 for a system x equal to b, the right hand side is b is 0, then it is a homogeneous system. Generally, system is non-homogeneous. This non-homogeneous linear system, whenever a system we are mentioning, say a system equal to say Ax equal to B, A is a matrix, X is a vector, and right hand side B is also a vector. So this system, sometimes we say system is consistent, sometimes we say the system is inconsistent. Either system is consistent or inconsistent. If the system is consistent, it has solution. So this solution may be unique or may be infinite. If the system is inconsistent, then there is no solution. So this we know from the system of linear equation. So here same method we are going to use. The linear programming problem. In general, the linear programming problem, sometimes we say it has solution. The solution is unique or solution is infinite, or sometimes this linear system has no, the linear programming problem has no solution. So whatever we observe for the linear system, same things for the linear programming problem. Okay. Is it okay? Hello? Are you able to hear? Or any problem?
Yes.
So all the students you have joined? All you have joined or not? Or anybody who is waiting? Okay. See, now I'm coming to next model, that is linear programming LPP problem. This is model 3. Say what we are doing in the model 3. See, you see, we have a linear programming model. So if you compare 1, 2, 3, earlier I have taken these are inequation. This LPP model 1, all these constants, this this equation 5, there are m number of constants. All these constants are inequation. That is, this less than equal type inequations are known as type 1 inequation. There are m number of type 1 inequation. So type 1. Similarly, so if you go to the model 2, there are m number of greater than equal type inequation. These are known as type 2 inequation. So type 1 inequation and type 2 inequation. There are two types, greater than equal type and less than equal type. Generally, in the minimization type problem, we use greater than equal type constants. In the maximization type problem, we use less than equal type constants. It may happen. So all type of constants are also available in a maximization type problem. All type of constants are also available in a minimization type problem. This may also happen. So we will take care of such model also. So this third model, I am considering a linear programming model. So all the constants are equation. All the constants are equation. Okay. So what we are finding here? So we have an objective function we like to maximize, subject to constants. So there are say m number of constants. Now some restriction is imposed on m and n. This n and m, they may be equal, they may not be equal. N, generally n is greater than m, or sometimes n is less than m also, it may happen. But if n equal to m, you see, n equal to m, we have a system of linear equation. So if you are saying n equal to m, it looks like a square system. Square system means number of variable equal to number of equation. number of variables equal to number of equation. If number of variable equal to number of equation, in case this system is consistent and it has only one solution, unique solution, then this problem has only one solution. So in this case, nothing to do. So whatever solution we are finding, that is the optimal solution. I am repeating again. If you find a problem like this, number of equation and number of variables are same, the system is consistent and system has only one solution, then the optimal solution is that solution that is unique. Okay, so only one solution. So simply you solve the system and whatever solution you are finding, that is the optimal solution. Okay, but generally, since n is more than m, generally this number of unknowns, number of variables, what we are saying x1, x2, xn, generally they are more than the number of equation. So this, it may not happen always. In some cases it may happen. Say number of equation equal to number of unknown, then we'll have, if system is consistent, we have only unique solution, that is the optimal solution. Similarly, now come to the number 4, model number 4. So we have a minimization type objective function. We have a minimization type objective function, and the constants, you know, all the constants are equation. They are not inequation, they are equation. So if we are finding the number of variable equal to number of equation and the system is consistent, it has only one solution, if I am saying, then this minimum solution, the optimal solution, whatever we find for this problem, that is the solution of the system, only one solution. But please remember, there is restriction. What is the restriction? All the decision variables are non-negative. All the decision variables are non-negative. So if there is a system, if you solve it arbitrarily using the method whatever you have learned, the solution may not be always non-negative. So that solution, whatever we are looking for, that has to be non-negative. Why non-negative? Generally, these variables, I can say, that is the x1, I can say number of in a building, say I'm saying the size of a door, okay, length, breadth, height, etc. Okay, the thickness. So this cannot be negative in positive terms. The number of experts needed, or number of managers or number of engineers required for a project needed. So that has to be a whole number sometimes, you know. So the number, it cannot be negative. Okay, so this x1, x2 up to xn, these are the variables are known as the control variables. It has to be non-negative. Okay, so see the model 4, model 3, they are the two typical models. So and specifically we have taken equation. The constants are simply equations instead of inequation. And so this is also representing linear programming models. We like to find the solution of such models. So next. So here generally, whenever there is a inequation, see this is a inequation. Summation over j varies from 1 to n, aij xj less than or equal to bi, and the bi is non-negative. This is a inequation. This inequation is known as type 1 inequation. This inequation is known as type 1 inequation. So if the type 1 inequation is there, so if you want to convert it to an equation, we have to introduce a slack variable. So for this inequation, we introduce a slack variables. These slack variables, there are n number of such variables, and one more you are adding. So we are naming as xn plus I. This is slack variables. So once you are adding the slack variables, this is becoming equation, and this is equal to bi. Right hand side is bi. Bi, of course, we are saying non-negative. This xn plus y is also non-negative. This is we are treating as a slack variable. Okay, so we introduce a slack variables in this case to convert a inequation, that is a type 1 inequation. Okay, to convert to equation, we introduce slack variables. That's all. Similarly, so if there is a type 2 inequation, type 2 inequation means this inequation is greater than equal type. What do we do? So if there is a type 2 inequation, we subtract something, then we add something. Okay, so whatever we are subtracting, that is xn plus y, you are subtracting, that is known as surplus variable. And whatever you are adding, why there is a requirement of adding? Because this surplus variable cannot be act as a basic variable in a linear programming problem. Only slack variable or a artificial variable can be a basic variable. Surplus variable cannot be a basic variable. So once you are introducing the surplus variable, there is a need of adding an artificial variables to this inequation. So as a result, we are writing in this form summation over j varies from 1 to n aij xj minus xn plus I plus xn plus I plus 1 more, then equal to bi. So what do we observe? If it is a type 1 inequation, we add a surplus variable. If it is a type 2 inequation, we subtract something, then we add something. Whatever you are subtracting, that is known as surplus variable. Whatever you are adding, that is known as artificial variables. For this type of constraints, two variables are needed. One is known as surplus variable, other is known as artificial variables. Okay, this. Why we are doing like this? Because we have to change all the inequation to equation. Then you can solve. Whatever constants are there, they are sometimes equation or inequation. We have to change all these inequations to equation, then you have to solve. Okay, so see further, if we have a constants of equation type, if we have a constants of equation type, there is no need of adding anything. But if this is there in a linear programming problem, if it is there in a linear programming problem, we have to add an artificial variables. These artificial variables, whatever you are adding, artificially you are adding, its value has to be 0. So in our method, we have to drive out these artificial variables. If we cannot drive out these artificial variables, then we can say the problem is infeasible. We will discuss about that in detail. So please remember, so if there is a equation in a linear programming problem, so there you have to add an artificial variables. So in general, we have a inequation in a linear programming problem. So if there is an inequation, we add a slack variable. If there is an inequation of type 2, then we subtract a surplus variable, then add an artificial variables. If there is an equation, we also add an artificial variables. This we have to do to solve a linear programming problem. Okay, so hello.
Hello. So I have a doubt.
Yes, please.
So why are we adding the artificial variable in the equation case? Wouldn't that be redundant since you said that anyway we'll be setting it to 0?
Yes, yes, yes. See, uh, I have told you something. Okay, you this see this problem here. This model 3, model 3 and model 4. Model 3 and model 4, what is there? Model 3 and model 4, what is
We have
there?
equations.
Equation.
Yes.
So let us say, make a very simple thing here. Make us say the system is consistent, it has solution. Okay. So the system is consistent, it has solution. If you solve this problem, what is the guarantee that you will get all the decision variable non-negative? Is there any guarantee?
No.
There is no guarantee. Okay. So there is no guarantee that this solution will be non-negative. So here, so whatever you are adding, the slack variable, surplus variable, artificial variable, whatever you are adding, so this has some purpose. What is the purpose? So if there is a constraint, with respect to that constraint, we introduce a basic variable. That basic variable has to be always non-negative. Okay. So we try the solution using the basic variables. Here, simply nothing is done. So we have a system. So we will solve it. If you find locally all these decision variables are non-negative, then we say it is a solution. Okay. But what is the guarantee that they will be non-negative? There
Okay,
is
so
no
it
guarantee.
bias
Yes.
the values up in a way to ensure that all the
Yes,
answers.
yes, yes. So please wait for some times, because only we have learned how to change this inequation to equation. Okay, it has some purpose. It has some purpose. So similarly, in this model 4, in the model 4, also we have, see the last line. So if I will drop this last line, then any solution will do. But generally, so in the linear programming model, all the decision variable has to be non-negative. There is restriction we have imposed. But if you solve a system, what is the guarantee that this solution is non-negative? There is no guarantee. But here we were imposing this extra restriction. Say all the decision variable has to be non-negative. Okay. So this, after introducing slack, surplus, artificial variables, now our problem we are naming as the LPP model B. Either it looks in this form, you see here. Now I have already introduced slack, surplus, artificial variables. So once you have introduced slack, surplus, artificial variables, earlier there are small n number of variables, Now we have capital N number of variables. Okay, this capital N number of variables. So now nothing is mentioned. Okay, nothing is mentioned. So how many constraints are? Earlier it was less than equal type. How many are greater than equal type? How many are equal type? Nothing is mentioned. So after introducing slack, surplus, artificial variables, these problems may be formed in this form. This is one form, or maybe a minimization form. So minimize Z, that is summation over J varies from 1 to n, Cjxj, subject to J varies from 1 to n, Aijxj equal to Bi, and this. Okay, these are the two forms. So we like to find solution for this type of problem. Okay, so we like to find solution for this type of problem. Specifically, I mentioned the number of variable, now it is capital N. This capital N includes actual variable, small n in number. Then we have slack variables, depends on the problem. Then we have surplus variable. Then we have artificial variables. But among the capital N number of variables, there will be small m number of basic variables. Which will be basic variables? I will mention. The slack variable can be basic variable. An artificial variable can be basic variable. a surplus variable cannot be basic variable. The reason is, if I am saying here the surplus variable cannot be a basic variable, the reason is like this. You can see here. So in case I am setting, as you know, the artificial variables artificially added, artificial variable, let us say it is not there. It is a type 2 in equation. The artificial variable, somebody by mistake, he has not added the artificial variable. Simply he has subtracted the surplus variable and it is becoming, so summation over j varies from 1 to n aij xj minus xn plus I equal to bi. This artificial variable is not there. See, now I am setting, let us say x1, x2 up to xn, all are 0. If I am setting these are all 0, then what will happen to this problem? Minus xn plus I equal to bi. Already this is given, bi is non-negative. So minus of xn plus I equal to bi. So as a result, xn plus I is becoming negative, which is not permitted. So this surplus variable cannot be a basic variable. This is the reason, because there is negative sign and right hand side is positive. So if all are becoming 0, then it is becoming negative. So it has to be, all the variables has to be in general non-negative, but it is becoming negative, so it is not permitted. So this cannot be a basic variable. Surplus variable cannot be a basic variable. Okay, that's all.
Sir.
Yes.
Sir, in the LPP 5 which you showed,
Yes, right.
the
Tell me.
how did the constraint change for maximization objective? Like initially we had small n number of variables, and how did it become
small n? The constant, you see. So if this, some terms in the objective function, in some terms, I can say after xn, say like say c1 x1, c2 plus c2 x2 plus c3 x3, then plus cn xn, then 0 into xn plus 1 plus 0 into, because that is not there, no? The coefficients are not there. So it is 0. I can say, I can write some are 0. Okay. But generally, so there is some technical problem because I told we have introduced some artificial variables. These artificial variables we have to remove. So since you are going to remove the artificial variable, so we have to introduce some weight to drive out the artificial variables. So that will be discussed in chance method of penalty or called big M methods. So we'll discuss. Okay. So please wait. So see, just I have mentioned how to transform this model to another model. So the model, in the model we have all equation. Okay. So this is a standard models which will be used to solve in the linear programming problem. This type of model V or model VI to be used. So that will be discussed. Okay. Now, so very quickly I am talking about the solution. The reason is like that because after sometimes you will have the laboratory. In the laboratory you will write some code. So all the theory slowly will cover. So these are the methods generally we solve in the linear programming. First one is the graphical methods. I hope all of you know. So still we'll discuss about the graphical method. Next is the simplex method. And this is also known as primal simplex method. The third method is known as big M methods. So this M, so this is a penalty. So that is defined in the chance penalty method. So this penalty we use to drive out the artificial variables. So this number 4, that is two-phase simplex method. This two-phase simplex method is an alternative methods for the big M method. Then we have dual simplex method. So since there is a primal simplex method, then we have with respect to primal, we have a dual simplex method. Then there is a combined method known as primal dual simplex method that also will be discussed. The next one is the revised simplex method. The last one is the interior point method by Narendra Karmakar. So I will request everybody, please, from the internet, you read about the linear programming, and the last one is what is called interior point method. Okay, this method is quite different from the simplex method. So we must know what is called interior point method. So please go through this last method. Okay, so I will also provide you some documents, whatever I have, but please go through so that you learn little more about the interior point method. Okay, these are the methods. So mainly we'll discuss. So one by one, all the methods. See, before this method, so I was telling about the basic solution. There is the system of linear equation, you have solution. So with respect to solution, we have the basic solution. Then we have also a basic feasible solution. Now we'll discuss about the basic solution little. So before going to the method, okay. So see here, generally, we have learned how to solve a system of linear equation that is in the form A into X equal to B. So what is capital A? This is a matrix of size m by n. There are m number of row and n number of column. X is a vector. This has components like x1, x2, xn. Then B is a vector. It has components like b1, b2 up to bm. This we are naming the system as Ax equal to B. So in general, it has m linear equation, and there are say n variables. These variables, nothing is mentioned whether they are negative or positive or zero. Nothing is mentioned. They are variables. Okay, and as you know, so whenever we are finding the solution, we are checking whether the system is consistent or inconsistent. So under what condition system is consistent? The system is consistent, we say rank of the coefficient matrix equal to also the rank of the augmented matrix, both are equal, and it is given, and this n number of variables is more than the number of equation. Okay, so here the condition is the system is consistent and number of variables is more than the number of equation. See, what do you observe? This consistent and more variables are there. Then it indicates this system has solution, but the solutions are infinite. But if you find this is a square system, the rank of the coefficient matrix is also equal to the rank of the augmented matrix equal to n. Square system, then you have unique solution. But since this is a consistent system and the number of variables is more than the number of n, this has more than number of m, then it has infinite number of solution. Okay, so here let us say the rank of the coefficient matrix A equal to small m. This m, let me say it is strictly less than n. That is, rank of A is m and m is less than n. And we are looking for the basic solution. Basic solution. Say, so we have to define what is called basic solution. Say, there are n number of variables. Out of n number of variables, see, rank equal to m. Let me say, I am talking about the m variables. first m variables, x1, x2, xm. These are the variables. Let me say these are my basic variables, and I'm expecting their value has to be non-zero. Out of n, this I'm saying at non-zero, then there are how many variables left out? That is n minus m variables. Let me say they are all zero. Two categories, some are non-zero, some are zero. So after that, if you set in this manner, the system Ax equal to B, as soon as you are setting some of the variables 0 and some are non-zero, the Ax equal to B becomes something like B into XB. The capital A is becoming capital B. Our X means the solution vector. This X is becoming XB. Right hand side B remain as it is. So this is becoming a system, looks like a square system. This square system is solvable if the determinant of this matrix B is non-zero. If it has solution, let us say this has solution, our XB you can write as capital B inverse into B. This XB is called basic solution. Now it is clear how to find basic solution. See, consider the system Ax equal to B. We have decided here the number of variables are more than the number of equation. Now we are finding the rank of this coefficient matrix. Okay, and so this rank, let me say equal to m, and system is consistent. Say once it is consistent, we say it has infinite number of solution. So out of this n variables, this m variables we are setting say non-zero, rest n minus m variables 0. So this system Ax equal to B is becoming B into XB equal to B, and this is solvable, let us say. If it has a solution, then XB equal to capital B inverse into B. This XB is called the basic solution. And here maximum possible basic solution, that is NCM, the same as NC n minus m also. So this is maximum number of basic solution you can find from the system. Okay, this. So I am just citing a small example to clarify this point. Small example. Okay, see this system Ax equal to B. This system Ax equal to B. If you observe how many, there are two equation. First one is x1 plus x2 plus x3 equal to 10. Second one, x1 plus 4x2 plus x4 equal to 16. Actually, this I have considered from a linear programming problem. Later on also, you will see that this same problem we are solving. So you can compare, say, what is the difference, what solution we have obtained here and what solution we have obtained there. Okay, so if you solve using the linear programming technique, okay, this x1 plus x2 plus x3 equal to 10, x1 plus 4x2 plus x4 equal to 16. How many variables are here? Can you tell me how many variables?
4.
4 variables. Then how many equations are there?
2.
There are 2 equations. Okay. See, I like to mention here. So it was actually initially it was given x1 plus x2 less than equal to 10. So we have added in the first equation x3. This x3 is acting like a slack variables. In the second equation it was x1 plus 4x2 less than equal to 16. So I am adding here x4 to make it equation. This x3 and x4 looks like they are slack variable. Okay, but here don't think anything about the slack variable, surplus variable, artificial variable, nothing. So these are only 2 linear equation. There are 4 variables. Okay, so but if you realize, so this x3, x4, so this was 2 in equation, so I have changed to equation. As a result, this x3 and x4, they are becoming our slug variables, but here nothing. Okay, these are 2 equation only. So are there is there any restriction on these variables? Is there any restriction? No restriction. No restriction. Now, so if you calculate the rank of the coefficient matrix, what should be the rank of the coefficient matrix here?
2.
And rank of the augmented matrix? Also 2. Rank of the coefficient matrix 2. Rank of the augmented matrix 2. So it has solution. This system has solution, and the solution is infinite. It cannot be finite. It has infinite solution. System is consistent. Okay. Now, say out of 4, since we have the number of variable equal to 4, and the rank of the coefficient matrix A equal to 2, so we will select out of 4 2 variables, non-zero and 2 are 0. 2 are non-zero, 2 are 0. How many way you can select? How many way you can select?
4C2.
4C2, 6 ways, clear cuts. Okay, so this 6 maximum possible solution. So if you are selecting in this, so there will be 6 maximum. Okay, not more than 6. Okay, 6 way you can select. So now we are going to solve it. See here, please remember x1 plus x2 plus x3 equal to 10, x1 plus 4x2 plus x4 equal to 16. This, okay. It's very easy to remember these 2 equations. Now, these 6 ways I have just mentioned in this manner. So, first non-basic, then basic. Okay, non-basic, basic. So, these 2 x1, x2, 0, I am setting once. Then x1, x3, 0, second time. Third time x1, x4, 0. Then fourth time x2, x3, 0. Then fifth time x2, x4, 0. Then sixth time x3, x4, 0. Okay, this is the enumeration. Okay, so some way to calculate. Okay, so once I am setting x1, 0, x2, 0, x1, 0, x2, 0. So what is the solution? x1, 0, x2, 0. What is the solution? So x3 equal to 10, x4 equal to 16. If you are setting x1 equal to 0, x2 equal to 0, this x3 is becoming 10, then x4 is becoming 16. This is solution. So what is the solution? We are writing here. So x1 0, x2 0, x3 10, x4 16. See here. So the first serial number 1, you can see here, the non-basic variable x1 is 0, x2 is 0. There are 2 are non-basic variables. If the 2 are non-basic variable out of 4, the 2 are the basic variable. The basic variable x3 and x4, they are becoming 10 and 16. So this is a solution. Here we find the basic variable, non-basic variables are, 0 means non-negative. Basic variables here, they are also non-negative. So all the variables are non-negative. All the variables are non-negative. So the serial number 1, whatever solution you have obtained, this is a basic feasible solution of the system. Feasible means all are non-negative. Clear? All are becoming non-negative. This. Now, come to the serial number 2. Serial number 2, x1 0, x3 0. These 2 are the non-basic variable. x1 0, x3 0. So x1 0, x3 0. Say what is becoming x2? X2 becoming 10. Once x2 is becoming 10, say x1 already I have mentioned 0, then What about the x4? That is 40 minus something, it should be. So x4 is becoming 24. So minus 24. So you can see here. So second time, once you're setting x1 equal to 0 and x3 equal to 0, we are finding x2 equal to 10 and x4 equal to minus 24. The non-basic variables are non-negative. What's two basic variables, whatever we are finding, one of them is positive, another is negative. So this cannot be this is a solution. This is a basic solution, but this cannot be a basic feasible solution because one of them is negative. Similarly, third one, x1 0, x4 0. So x2 4, x3 6. This is a basic solution. This is also a basic feasible solution. Number 4, x2 0, x3 0. We are finding x1 equal to 10 and x4 equal to 6. So this is a basic solution. This is also a basic feasible solution. Fifth one, x2 equal to 0, x4 equal to 0. So we are finding x1 equal to 16, then x3 equal to minus 6. This is a basic solution, but this cannot be a basic feasible solution because one of them is negative, x3 equal to minus 6. The last one. So x3 equal to 0, x4 equal to 0. We are finding x1 equal to 8, x2 equal to 2. The sixth one is a basic solution. This is also a basic feasible solution. Now the conclusion is like this. Out of the 6 solutions, 2 of them, which one? The serial number 2 and serial number 5, they are not basic feasible solution. Basic feasible solution because one component is becoming negative. So they are basic solution, but only out of 6, 4 of them are basic feasible solution. But in a linear programming problem, whatever solution you are finding, that has to be a basic solution as well as a basic feasible solution. Basic feasible means all the component has to be non-negative. If you find some of the component is becoming negative, that cannot be a basic feasible solution. That is the conclusion. Is all right or any confusion? Hello?
Sir, I have a doubt.
Yes?
Sir, suppose we set some variables to 0, then it
Yes.
might also happen that the system becomes inconsistent or we have infinitely many solutions.
See, we will have some example also. I will mention some example. Okay. So where you find, say, after setting that equal to 0, so you say that it is becoming inconsistent once you set. Okay. See, we are not doing that. What we are doing? We are exploring the basic feasible solution. Okay. So how to explore the basic feasible solution? We consider a system first. Okay. Then you check whether the system is consistent or inconsistent. We find the system is consistent. And generally, we have more number of variables and less number of equations. Okay. So after checking that the system is consistent, we find the coefficient matrix, rank of the coefficient matrix. So see, if you find the coefficient matrix rank equal to, let us say 2, then what we are doing? Then out of n variables, say 2 of them, let us say non-zero. 2 of them non-zero. So then rest we are setting up 0. Then we are trying to explore the solution. It may happen, say when we try to explore, so there is no solution also. So if there is no solution, that case we cannot consider as a case for basic feasible solution. But here luckily all the 6 cases we have solution. They are basic solution, but they are not basic feasible solution. Only out of 6 cases, 2 are not basic feasible solution, rest are all basic feasible solution. Okay, right?
Okay, sir.
See, some definitions I'm just again stating. So actually this is required also. So what is this? Because generally we are solving linear programming problem. So of n variables, there are say n such variables. Okay. So when you say that x is a point, this has a n number of components. These are the coordinates also, you can say this. So with respect to these components, these coordinates, this in the linear programming problem, all the component has to be non-negative. Okay, this. So this definitions will come to see. Now we are talking about the line segment. What is a line segment? Now let us consider two different points. Okay, so in the n-dimensional space, A is a point. Okay, it has coordinates. Okay, this coordinates, since the coordinate has something like say x1, x2, xn, x1, x2, x3, x up to xn, but we are writing vector notation x1. Okay, so this x1 has n number of components. Similarly, so let's say the coordinate of B, the point B equal to x2. This x2 has also n number of components. Now we are talking about the line segment. Line segment means line joining this point A and B. So if you join these 2 points A and B, we have a line segment. So how to define the line segment? How to define the line segment? So in mathematically, line segment, we are saying L. So L is the line segment. So this x, this is a function of lambda. So lambda, this x lambda is becoming lambda times x1 plus 1 minus lambda times x2. What about lambda? Lambda varies in the interval, the closed interval 0 and 1. Okay, this. So, right? For example, so let me say 2 points. So 2 points, let us say first point is, let us say x1, x2. And second point, say, let us say some other point, say y1, y2. Okay, say x1, x2, or I can write say x1, y1 or x2, y2. This. So lambda times this first point plus 1 minus lambda times the second point. Okay, so what about lambda? Lambda varies in the interval 0 and 1. So this gives the line segment. Why line segment? Why we are introducing line segment? See, generally, say whenever you are solving a system, so whenever solving a system, we are finding solution. Okay, these solutions, some solutions are called basic solution and some solutions are called basic feasible solution. Okay, these basic feasible solutions are nothing but the extreme points of the convex set. Extreme points of the convex set. Okay, extreme points. And generally, our optimal solution occurs at the extreme point only. Okay, so we are looking for the extreme points. And if you find there are 2 different extreme points, they are acting as the optimal solution, then the line joining the 2 points A and B. So this line segment, the entire line segment, the points on the entire line segment is also the optimal solution. In that case, you will find infinite number of optimal solution. Okay, this again we will repeat it. Okay, when there is some numerical example or something like that. Okay, so this definition again I will repeat. I am coming to
Sir,
yes.
sir, why was the lambda restricted to 0 to 1 in that case?
Repeat it again. Please repeat.
Sir, why
Yes.
was lambda restricted to 0 to 1?
See, 0 to 1. You are right. You are right. Why you are asking? Okay. Why it is restricted? There are two different points. See, once you said lambda equal to 0, what will happen? Lambda equal to 0. So 0 into x1, this is gone. This x is becoming x2, right? These two ends, one end is x1, other end is x2. Once I'm setting lambda equal to 0, this other end, the point is becoming, x is becoming b. Once I'm setting lambda equal to 1, this x is becoming a. Okay. So once x is becoming x2, another x is becoming x1. 2 points. So if you are considering this, lambda in between, let me say lambda equal to half. Then what will happen to this? So you will find the middle point. You say lambda equal to 1/3. Okay. Lambda equal to 1/3, then one side 1/3, another is 2/3. So some points. So these two extreme points are, say, lambda equal to 0, one extreme point, that is x2, lambda equal to 1, another extreme point, that is x1. That's all. You can see here. It is clear, indeed.
Yes, sir. Yes, sir. Thank you.
Two extreme points. One is with respect to lambda equal to 0, that is our x2. So one is with respect to lambda equal to 1, that is x1. Two extreme points. X is either x1 or x2. But if you consider lambda equal to half or 1/3 or 1/4, then you will find the point in between x1 and x2. Okay. There are infinite number of points. Okay. So on the line segment AB, there are infinite number of points you can find. So using this formula, that's all. See, we are talking about the extreme point. Extreme point in the convex set S, which does not lie on a line segment joining two other points of the set. Say we are saying extreme points. So I have already mentioned the line segment, line joining this point A and B, line segment. So A is an extreme point, B is an extreme point. All the other points are on the line segment. So extreme point means, so in a convex set, the extreme point means it is a point which does not lie on the line segment of other 2 points. Extreme points, either it is point A or point B. So other than these 2 points, all are on the line segment. Now we are talking about the feasible solution. In a linear programming problem, any solution x which satisfy this equation Ax equal to b and x is non-negative is called a feasible solution. Again, I am repeating. So in a linear programming problem, any solution which satisfy this equation Ax equal to b and x is non-negative is called a feasible solution. See, I have already mentioned earlier the basic solution. This is a solution in which n minus m number of variables are set equal to 0 in the system Ax equal to b. It has m equation and n unknowns. N is more than m. So we are finding the basic solution in this manner. Basis, the collection of basic variables which are not equal to 0, to obtain the basic solution is called the basis. The collection of basic variables which are not equal to 0, okay, not equal to 0, to obtain the basic solution is called the basis. Okay, this. We have something like, say, basic feasible solution. I have also repeated. the basic solution which will satisfy the condition x is non-negative is called the basic feasible solution. See, in the basic feasible solution, it may happen there is some components, the two parts, basic variable, non-basic variables. All the non-basic variables are 0. Basic variables generally they are non-negative, 0 or positive. If you find all the basic variables are positive, then it is called a non-degenerate basic feasible solution. It is a basic feasible solution which has exactly m positive values out of n. The optimal solution say this is a basic feasible solution which will optimize, means either maximize or minimize the objective function, is called the optimal solution. Means basic feasible solution is nothing but our optimal solution. See, some theorems I will not discuss now. I will repeat again. Okay. So now, because why I am doing so? Because we know we want to solve some linear programming problem using the knowledge what I have told you or what I have gathered earlier. So using that knowledge, we like to solve some linear programming problem. Then again, we'll come to the theorem. Why? This theorem has to be learned thoroughly because these theorems are the foundation of the linear programming problem. Okay. First theorem. What is the theorem? This intersection of any number of convex set is also convex. I will give the proof. Okay. So theorem 2. What is the theorem 2? The feasible region of a linear programming problem form a convex set. Theorem 2. So theorem 3. The theorem 3 says that, so in a linear programming problem, okay, it has either one optimal solution or no optimal solution or infinite number of optimal solution. Any local maximum solution is also a global maximum solution for this maximization type linear programming problem. Similarly, theorem 3b, in general, a linear programming problem has either one optimal solution or no optimal solution or infinite number of optimal solution. So any local minimum solution of a linear programming problem is also a global minimum solution. So this is a minimization type problem. So this x star is the minimizing point. So theorem 4. This theorem 4 is very crucial. We will like to discuss also later. Every basic feasible solution is an extreme points of the convex set of the feasible region. Say we are looking for the basic feasible solution. This basic feasible solution is nothing but an extreme point of the convex set of the feasible region. Theorem 4. Then theorem 5. What is theorem 5? Theorem 5 says if S is a closed bounded convex polyhedron with p number of extreme points, then any point x can be written as x equal to summation over I varies from 1 to p lambda I xi, where I varies from 1 to p lambda I equal to 1 and the lambda is non-negative. This earlier we have discussed for 2 points. Now we are talking about the n points because S is a closed bounded convex polyhedron with p number of extreme points. With respect to this is the result. Okay. This theorem 6. Theorem 6 says let S be a closed convex polyhedron, then the minimum of the linear function over the convex set S is attained at an extreme point of the convex set. Similarly, so this is also true for the, similarly it is true for also for the, so maximum, when the maximum solution also occurs at the extreme points. Okay. So very quickly, I am going through the graphical method, then the simplex method. So again, we'll return to this whenever there is a requirement. Okay. So
Sir,
the graphical methods, you know it, the graphical methods. I will simply give the summary. Say when there is a linear programming problem, generally, of course, we solve linear programming problem with two variables using the graphical method. Say what are the steps? Steps are like this. Say we define the coordinate system. Say there are two variables. So x1, x2, one for the x-axis, another for the y-axis. Define the coordinate system and we plot the axis. Associate each axis with a variable. Step 2, plot the constraints. Say when we plot, so either this constraint is a equation or an equation. A constraint represents either a line or a region, lower half or upper half. Step 3, identify the solution space, the feasible region. The feasible region is the intersection of all the constraints. If there is no feasible region, the problem is infeasible, there is no solution. The step 4, identify the extreme points of the feasible region. Say, see now the question is we are interested in identifying the extreme points. Why? The solution occurs at the extreme point only, nowhere else. Step 5, each extreme points determines the value of the objective function. Okay. For each extreme point, determine the value of the objective function. The point that maximizes or minimizes this value is called the optimal solution. Okay. So see this earlier we have taken systems to find the basic feasible solution. So one of the equation was x1 plus x2 plus x3 equal to 10. Another was x1 plus 4x2 plus x4 equal to 16. So in some way, I am not writing that. I am just solving a linear programming problem. What is the linear programming problem? We like to maximize this linear objective function z. Z is consisting of x1 plus 3x2, subject to x1 plus x2 less than equal to 10, and x1 plus 4x2 less than equal to 16, and this x1, x2 are non-negative. This. Okay. So this x1, x2 are non-negative. So earlier nothing was mentioned, so we are just exploring the solution, basic feasible solution. Here this is a complete problem. We like to find the maximum value of the objective function, and these are the restriction. Two constraints, both are inequation type 1 and x1, x2 are non-negative. See, since there are two variables x1, x2, so we'll name. So one is for x-axis, another for y-axis in this manner. Say this is the x-axis for the x1 and y-axis for the x2. See, x1 plus x2 less than equal to 10. Okay, this, if it is equal to 10, then it is a line. If it is less than equal to 10, it is a region. This region is below the line, including the line. Below the line, x plus x1 plus x2 equal to 10. As it is less than equal to 10 means below the line, the entire region. You can see here. So x1 plus x2 less than equal to 10. So this region is like this, below the line, all these points. Okay, all these points below the line, x1 plus x2 less than equal to 10. Okay, this. Okay, then the second one, x1 plus 4x2 less than equal to 16. So we will find the region below the line, x1 plus 4x2 equal to 16. So then we will take the intersection. This intersection, this is the region. The intersection is this is the region. This intersection. So if you consider the intersection and we find the value, one point is 0, 0. That is the, as you know, this origin is 0, 0. Another point is A. The coordinate is 10 and 0. Another point is C. The coordinate is 0 and 4. Another point, that is B, that is 8 and 2. This. So it has 1, 2, 3, 4. How many extreme points? It has 4 extreme points. So this intersection, the feasible region, this feasible region has 4 extreme points. One is O, another is A, another is B, another is C. This 0 and 10, this is cannot be an extreme points. This is outside the feasible region, 0 and 10. See why it is outside the feasible region, 0 and 10. So 0 and 10, this fulfills this one, first one, and 0 and 10 you can see, put x1 equal to 0, x2 equal to 10. So this is becoming 40. 40 cannot be less than 16, it is more than, so it is not fulfilling. So this is the feasible region. Okay, this feasible region has 4 extreme points, 0, then we have A, then it is B, then it's C. See, I have already mentioned these extreme points are nothing but the, basic feasible solution. These extreme points are nothing but the basic feasible solution. The solution occurs at the extreme points only. Okay, optimal solution occurs at the extreme points only. 0, 0. At 0, 0, what is the value? At 0, 0, the value is becoming z equal to 0. At 10, 0, value of the auxiliary function is becoming 10. At 8, 2, the value of the auxiliary function is becoming 14. Then at 0, 4, the value of the auxiliary function is becoming 12. This, and the maximum value occurs at the point P, that is 8 and 2. 8 and 2. Okay, this. See, there are 4 points we have got, 0, 0, 10, 0, 8, 2, 0, 4. These 4 points are the extreme points. These 4 points are the basic feasible solution. Now I am going to this example what we have discussed. I'm going to the example what we have discussed. Okay. This. Say what is happening this? 1. So x1 0, x2 0, x3 10, x4 16. Okay. There are 4 coordinates, but since you have drawn graphically, it has only 2 coordinates. Okay. Say 2 coordinates, x1 0, x2 0. So the first one is a basic feasible solution. Yes or no? First one is a basic feasible solution.
Yes, sir.
Yes, sir.
Yes. So this is our 0, 0, x1 0, x2 0. That is nothing but the origin O. Yes or no? Second one, since one component is negative, so second one cannot be a basic feasible solution. We drop. Third one, Third one, see, x1 0, x4 0, x2 4, x3 6. We need only x1 and x2, no other. Say if you consider only x1, x2, we find x1 equal to 0, x2 equal to 4. Okay, x1 equal to 0, x2 equal to 4. So this is corresponding to point C. Yes or no? Point C. Is it a basic feasible solution? Is it a basic feasible solution?
Yes, sir.
Yes. So the first one, serial number 1, was also a basic feasible solution that correspond to the extreme points. Serial number 3 is a basic feasible solution. This corresponds to the extreme point C. Now coming to serial number 4. So x2 0, x3 0, x1 10, then x4 6. We need only x1 and x2. So as a result, we are finding x1 equal to 10 and x2 equal to 0. Is it a basic feasible solution? Yes, it is a basic feasible solution. This is corresponding to extreme point A. So this is done. So serial number 4 is corresponding to the extreme point A. Now serial number 5, one component is negative. Is it a basic feasible solution? Is it a basic feasible solution?
No, sir.
Because there is one negative. So this cannot be a basic feasible solution. Serial number 6. So if you see serial number 6, so all the 4 components are non-negative. It is a basic feasible solution. So x1 equal to 8, x2 equal to 2. So this is corresponding to the extreme point B. Yes or no? Origin, first serial number 1, origin. Serial number 3, that is the extreme point C. Serial number 4, this is extreme point A. Then the last one, the serial number 6, extreme point B. See here, as you observe, these 4 basic feasible solutions, are nothing but the 4 different extreme points. One is 0 0, another is 10 0, another is 8 2, another is 0 4. So these are the 4 extreme points. So that is the reason we are searching solution at the extreme point only, nowhere else. So here this point is 8 2, this is 10 0, this is 0 0, this is 0 4. 4 extreme points, and at B we find it has maximum solution. So maximum value is becoming 14. In that problem, there was no objective function. It was given only find the basic feasible solution. That basic feasible solution, we are verifying whether that extreme point, whatever we have obtained, is a basic feasible solution or not. It is a basic feasible solution. Okay. Now, in case you are looking for the minimum solution for this problem, what is the minimum value? Instead of maximum, this is, let us say, we want to find the minimum value. What is the minimum value? Minimum value of Z equal to 0. At origin 0 0, it is minimum. See, once I am writing this, find the minimum value of this problem, minimum value of this problem, minimum value of Z, the minimum value becoming 0, but this is a trivial problem. So without solving, one can say that the minimum is 0. Okay. So because this is the, this is the first quadrant, we are searching solution at 0 0, it is becoming minimum. That's all. Okay. But if I am saying, so here instead of maximum, it is minimum, it is becoming 0, but maximum is the right statement. So once I am saying it is maximum, the problem is well formulated. If I'm saying it's minimum, the problem is not well formulated because it's between 0. Okay, that's all. Now I'm coming to the actual method that is called simplex method to solve the linear programming problem. So wherever there is a requirement, we'll again come to the theorem. All the theorems are very much useful. So if I'm repeating the theorem, you will not be able to realize how to find the solution. So once there is a requirement, we'll talk about that. Okay. So the simplex method, see, we like to maximize a objective function z, summation over j varies from 1 to n cj xj plus d. This d is a constant. This d I can simply drop it. I can say 0. Is it all right? Because we like to maximize. So in this problem, d is not there. x1 plus 3x2 plus d. D is not there. Let me say my d equal to 100. My d equal to 100. Then the maximum value z becoming x1 plus 3x2 plus 100. Say if d equal to 100, then what will happen to the solution? So this maximum value is becoming here 14. So we are adding one more 100. So then 14 plus 100. So this will be 114. Okay. So once I'm writing d here, so whatever the value, after obtaining the maximum, we can add that d. So since d is a constant, so it will not create any problem. Same thing here. The d is a arbitrary constant we have added here. Okay. So why we have added? The reason is you can see, and this constant something like summation over j varies from 1 to n, aij xj less than equal to bi. Okay. So something like right hand side value. So I have put here d. D generally it is 0. So if d nothing is there, it is 0. Then if it is there, same constant you can add. We like to maximize subject to this constant, and whatever these variables x1, x2, xn, they are non-negative. Our assumption, this b1, b2 up to bm, whatever is there in the right hand side, they are all non-negative. If this assumption is not there, there is some problem, because since they are all arbitrary constants, so we have to mention what is happening to the right hand side. The right hand side is strictly non-negative. So this is our assumption. So this problem we are formulating in this manner. See, you can see here summation over j varies from 1 to n, aij xj less than equal to bi. So technically for this, we have to add a slack variables. Yes or no? I have told you. So whenever this type of constants are there, we introduce a slack variable. So we are adding slack variable. So this is the first method. So it is quite different from others. So we will again rearrange so that everywhere you find the same logic, same rule we are using. See, then once you are saying I am adding a slack variables. So I am giving a new name. The slack variable, let me say, if I equal to 1, my slack variable equal to z1 plus z1. Z1 is non-negative. So this is equal to bi, or this you can see here, you take to the right hand side, summation over j varies from 1 to n, aij xj, this minus sign you take to the right hand side. So that is plus zi equal to bi. This is equal to bi. Is all right? So this I have arranged only. So our slack variable is nothing but our zi. Why we are writing in this form? Reason is, if you set all these x1, x2, xn are 0, then our zi is becoming bi. Zi is bi are non-negative. This zi is also becoming non-negative. This is our basic variable. Okay, this I varies from 1 to n. Can I write in this form? Please verify and tell me. Hello? See,
Yes, sir.
this Z1, Z2, whatever we are writing, they are all non-negative. Okay. So once we are presenting in this form, there are m such constants. So we will transform this constant to m such equations. Then we will put in a simplex table. Say, how do you put a simplex table? Let us know. So our table is like this. Okay. So the simplex table, what we are formulating. So see, with respect to the first constraints, say these are the first row, second row, etc. So I will mention here. So we are writing summation over j varies from 1 to n, aij xj plus bi equal to zi. There is a minus sign. Okay, minus sign in the reference side. So how do see here a11 into minus x1 plus a12 into minus x2 plus and so on. Say the last one a1n 1n and this will be minus xn. Let us say minus x1 minus x2 minus xv minus xn. Then last term b1 into 1 equal to z1. Is it all right? So with respect to this constraint, what we are writing here, this constraint, which is the equation. So you can see here a11 into minus x1, a12 into minus x2 and so on. Finally, b1 into 1 equal to z1. This. So similarly, second equation, a21 into x1 minus x1, a22 into minus x2, a2b into minus xb, and finally a2n into minus xn. This will be minus sign, so I will correct it. b2 into 1 equal to z2 in this manner. So same manner if you continue, the last row, last but one row, a m1 into minus x1, a m2 into minus x2, so a mn into minus xn, bm into 1 equal to zm. So the last row corresponding to the objective function minus c1 into x1 minus x1, that is c1 x1, minus c2 into x2 minus x2, that is c2 x2, and finally minus cn into minus xn, that is cn xn. So d into 1, that is d equal to z. Okay, so this is becoming our table. This is called the simplex table. So this simplex table, we like to use it to calculate the value, calculate the optimal value. We'll discuss how we are doing so. Are you able to hear? Hello?
Yes, sir.
Yes, sir.
This. So with respect to this, once I'm setting, let me say here, once I'm setting x1 0 here, x1 equal to x2 equal to xn, everything 0. Say all these variables are 0. So certainly this is also becoming an extreme point. Then the value of the non-basic variables are 0. See, in this problem, how many variables are involved? How many variables are there? Calculate how many variables. This Z1, Z2 up to Zm, these are the variables. I have put different name. basic variable, non-basic variables. Say x1, x2 up to xn, these are the variables, actual variables, and z1, z2 up to zm, these are the basic variables. Altogether, there are n plus m number of variables. So we have out of n plus m, so we have to select n are m are non-zero and rest are 0. So assuming the coefficient matrix has rank m and it has infinite number of solution, assuming that, so we have selected z1, z2 up to zm, they are non-zero, rest are 0. So if you set this x1, x2 up to xn, they are 0. So we are finding z1 equal to b1, z2 equal to b2, zu equal to bu, zm equal to bm. See, in this table itself, it is indicating. And with respect to that, what is the value of z? If everything is becoming 0, our z is becoming d. That's all. So this value of the basic variables are z1 equal to b1, z2 equal to b2, zm equal to bm. The value of the auxiliary function z is becoming d, and all these variables like x1, x2 up to xn, they are 0. This. So we are finding one extreme point from the first table itself. Okay, this. I will mention the steps of the simplex table. So simplex table or simplex algorithm. So the same problem, before showing the algorithm, I am just mentioning a small example. I will come to this. This is the problem you can see here. Maximize z equal to x1 plus 3x2, x1 plus x2 less than equal to 100, x1 plus 2x2 less than equal to 110, x1 plus 4x2 less than equal to 160, and this x1, x2, they are non-negative, and we are adding slug variables. Generally, it is right to add x1, x2. I can add x3, x4, x5. Instead of adding x1, x2, x3, x4, x5, I am adding z1, z2, z3 for a different purpose, because these are the actual variables x1, x2, and the slug variables are naming as z1, z2, z3, so that you can differentiate which one is a slug variable and which one so is the actual variables. So if you are adding in this manner x1 plus x2, then the slug variable z1 equal to 100. Is all right? With respect to the first inequation, so x1 plus x2 plus z1, this equal to 100. So once you are adding in this manner, so this will be, you can write, so x1 plus x2 plus z1 equal to 100, or you can write minus x1 minus x2 plus 100 equal to z1. Why you are doing in this form? As soon as I set x1, x2 0, our z1 equal to 100. Similarly, x1 plus 2x2 plus z2 equal to 110. So minus x1 plus minus 2x2 plus 110 equal to z2. And similarly, third one, x1 plus 4x2 plus z3 equal to 160. That is minus x1 minus 4x2 plus 160 equal to z3. And as you know, the objective function z equal to x1 plus 3x2. So nothing is there. So we'll set d equal to 0. Now the problem can be put in a tabular form. So how you can put in the tabular form? See the tabular form. This is the tabular form. Say 100. So we are writing in this form minus x1 minus x2 plus 100 equal to Z1. Second one, minus X1 minus 2X2 plus 110 equal to Z2. Third one, minus X1 minus 4X2 plus 160 equal to Z3. The last row represent the objective function. So this is minus 1 into minus X1. This is X1 minus 3 into minus X2. That is 3X2 plus 0 equal to Z. Can you write in this form? Please check. Hello?
Yes, sir.
See, now it is clear how we are presenting this problem in a tabular form. This is the table. Okay, this is the table. And what are the steps we are going to utilize? So I am going to the original algorithm. What is there? Step 1. So step 1 I have told, select the most negative element in the last row of the simplex table. If no negative element exists, then the maximum value of the linear programming problem is D, and maximizing point is X1 equal to 0, X2 equal to 0, up to Xn equal to 0. Stop the method. Okay. So with respect to our numerical example, this is the first table. The last row you can see here, last row minus 1, minus 3, etc. And this is of course the value of the D, Z equal to 0. So now we check, is there any negative element? Answer is yes. If instead of minus 1, minus 3, if it is plus 1, plus 3, then clearly we'll write the value of the objective function equal to 0. So nothing to do. But since there is a negative, two negative elements are there. So we are selecting the most negative element. Most negative element is minus 3. Okay. Most negative element is minus 3. So if there is a tie, for example, it is minus 1, minus 1. You can select either with respect to first column, with respect to second column, whatever. So here, since the most negative is minus 3, we will select the most negative element is minus 3 with respect to second column. Okay, this. Now, see the step, further step. Suppose in step 1, so we are finding, no, this is the select the most negative element in the last row of the simplex table. If no negative element exists, then the maximum value equal to D. Maximizing points, all are 0. Stop the method.
Sir, if D is more negative, then should we select D, or do we have to select only from this first n elements?
Repeat it again.
Sir, if D is more negative, then should we select it?
B. You are talking about B.
D.
No, see here, D is a constant. See, generally, so the D we will not bother if it's whether minus 100 or plus 100, hardly matter. It is a constant. This constant will not affect anything. Okay, so the D, so generally, so in our problem D equal to 0. For example, say instead of, say in this problem, say we want to write, say maximize Z equal to X1 plus 3X2 minus 100 or plus 100, hardly matter. So if you are adding plus 100, the optimum value becoming how much? See here, 114. If you are subtracting 100, that is 14 minus 100, that is 86, minus 86. Okay, so this will not affect. If it is 0, so this is becoming 14. So either if D is positive, that you add. If D is negative, that you subtract. If D is 0, nothing to do. Okay, so this D, for some reason we are, because that column in that box. So here something to be written here. either D equal to 0 or negative or positive, some constant. So okay, D is a constant. So if you use that constant, whatever the value, so after obtaining that you add or subtract accordingly. So if it is 0, nothing to do. Okay, let us say it is 0. Okay, right. So this will not affect anything to your problem. Okay, this other than D. So you will select, there are n number of columns, x1 column, x2 column, xn column. So you see in the last row what are the value. Choose the most negative value. If there is a tie, you can select anyone. So there is no problem. Okay, because our purpose is you will move from negative to positive. Okay. Step
Okay,
2. Suppose step 1 gives element minus CB at the bottom of the bth column that is available. Form all the positive ratio of the element in the last column corresponding to the element in the bth column. That is form ratio BI divided by AIV, for which the AIV is positive. The elements AUV, which produces the smallest ratio, BI divided by AUV, is called the key element or pivotal element. Okay, I am just explaining here. This is the table. This is the table. So now with respect to -1 and -3, most negative is -3. Okay, so second column is selected. Second column is selected. Now once you have selected the second column, so we find the ratio. Which way we find the ratio? 100 divided by 1. How much? 100 divided by 1. How much? 100. Then 110 divided by 2. That is 55. 160 divided by 4. That is 40. So whichever gives the minimum ratio, that is selected. So we are finding the minimum ratio is becoming, and this you can divide if this 1, 2, and 4 you are finding they are all positive. If you find one of them is negative or 0, you cannot divide. 0 certainly not, and if it is negative, we will not divide also. Only positive ratio you will find. 100 by 1 equal to 100, 110 by 2 that is 55, 160 by 4 that is 40. So we are finding minimum ratio is becoming 40. So this 4 is selected. This 4 is our key element. This 4 is our key element. Okay. So now once the key element is selected, how to proceed further? That I am telling. See, we have got a key element. Okay. So that is the pivotal element. If in case you find in that column all the elements are either negative or 0, then the problem is unbounded. For example, you find in this problem, this is -1, -2, -4. So we conclude that the problem is unbounded. So here all are positive. So that is the reason we are finding the positive ratio. If you find some elements are 0 or negative, so that is not permitted, only positive ratio. But if you find all are 0 or negative, then the conclusion is problem is unbounded. The problem is unbounded. Now next step, the step 3. What we should do? Once you have detected the key element, then we form a new table. In the new table, what we should do? The interchange the role of XB and ZU. That is, relabel the row and column of the pivotal element while keeping other label unchanged. I'm coming to this table. So this is the first table. So we have to draw a similar table. So in the similar table, what we'll do? So we have to give label. Here our labels are minus x1, minus x2, 1 for the rows, for the column, for the row, Z1, Z2, Z3 and Z. You can see here. Why it is so? So if you set x1, x2, 0, our Z1 equal to 100, Z2 equal to 110, Z3 equal to 160, Z equal to 0. Directly you can write. Okay. So now in this table, we have basic variable and the non-basic variable. Basic variable and the non-basic variables. What are the basic variable? Basic variables are Z1, Z2, Z3. These three are the basic variables. What are the non-basic variable? Non-basic variables are x1 and x2. And what is Z? Z is nothing but the value of the objective function. Okay. So out of the 4 rows, first row, second row, third row, these are telling something about the value of the basic variables. And with respect to x1, x2, they are telling about the value of the non-basic variable. And Z equal to 0 is saying something about the value of the objective function. Now, so we will relabel. Relabel in which manner we will relabel? See here. Say earlier I have told 100 by 1, 110 by 2, 160 by 4. So among this 160 by 4 is giving minimum ratio. So this 4 is our key element. There is a star mark I have put. So in the next table, you know, this is happening with respect to third row. This is happening with respect to third row and second column. Second column. In the next table, this Z3 will come to the X2 place and X2 will go to the Z3 place. So as a result, we will write here minus Z3 in the next table. So you will write minus Z3 and in place of Z3, you will write X2. So this is the labeling. So new label. In the new label, you will have here Z1, Z2. In place of Z3, you will have X2. Z remain as it is. So in the column label here, minus X1, minus Z3 and 1. Okay. So see here what we are doing. This is the label. Minus X1, minus Z3, 1 remain as it is, Z1, Z2, X2, Z. This, the labeling is over. Now, once labeling is over, say we are going to the next step. See, the step 3A, interchange the role of basic variable and non-basic variable. That is, relabel the row column of the key element, keeping other label unchanged. Then step 3B. What is step 3B? Replace the key element or the pivotal element by its reciprocal. By its reciprocal. So that is, so if it is P, this should be 1 over P. If it is U by V, then this should be 1 over U by V. Okay. So see here what changes we are making. So it was earlier 4. Earlier it was 4. So in the new table, this 4 is becoming reciprocal. That is 1 by 4. You can see here. So in place of 4, it is becoming 1 by 4. And what happened to the same row elements? So this 4 is becoming 1 by 4 and other elements you divide by 4. So this will be 1 by 4 and this 4 I have already told. This will happen 1 by 4, and 1 by 60 you are dividing by 4, this will be 40. The row elements 1 by 4, 1 by 4, 40 in the third row. So same thing here, you can see 1 by 4, 1 by 4, 40. And in the column elements, in the same column elements, you divide by 4 with a minus sign. This is minus 1 by 4, minus 2 by 4. This 4 is now completed. And this minus 3, it is becoming minus 3 by 4 with a minus sign, that is 3 by 4. So as a result, we have here, you can see minus 1 by 4, minus 2 by 4, 1 by 4, 3 by 4. So row and with respect to that column, the pivotal element, row and column, we have done it. So P is becoming 1 by 4, and for the particular row, you are dividing by 4, and for the particular column, we are dividing by the 4 with a minus sign. As a result, this is completed, and other than the row and column, this row and this column, there are several other elements. So how to tackle the other elements? So these other elements, we will apply this rule. See here, the B say that replace the key element by its reciprocal. C say that replace other elements of the row of the key element, row element divided by the key element, and replace the other elements of the column, negative of the column elements divided by the key elements, and replace the other elements, all other elements, using this formula. What is the formula? So we have S star equal to P into S minus Q into R divided by P. See, this P is our pivotal elements. For S, we want to calculate. We form a rectangle. So after forming the rectangle, we will just imagine a rectangle in this manner. So P into S minus Q into R divided by P. So for this S location, here we say the S star P into S minus Q into R by P. P into S minus Q into R by P. So as a result, we have the new table in this manner.
Sorry to interrupt, sir. We have actually other class. Can we leave?
Is over? Time is over. Okay. So you can move. I will stop here. Okay. Please, thank you. So we'll continue tomorrow from the same table. Okay, right? Please go through.